Welcome to MFC Group's FasTech Seminar series hosted by WestTech Sales. Thank you for joining us. Today we are spotlighting multi-time programmable PMICs from Qorvo. Our speaker for this seminar is John Alejandro. John is a seasoned marketing manager at Qorvo, where he leads the marketing strategy and execution for the analog power portfolio. Everyone's muted, so please feel free to put any questions you may have into the chat, and we'll monitor those and answer them at the end. And John, I will turn it over to you.
Thank you, Amanda. Again, my name is John Alejandro. I'm a marketing manager based out of Dallas, Texas, working for Qorvo. I've been total years at Qorvo. I've been at, roughly about 6 years, and then my previous tenure at Texas Instruments. But today I'll be talking about power management, analog power, more specifically about our PMIC portfolio. If you have any questions, feel free to put them in the chat, and then I'll go ahead and answer them at the end. All right. So if you don't already know what a PMIC is a culmination of power stages like a buck boost, LDOs, and then some level of logic control, right? With I2C registers or some amount of GPIOs. Inherently, PMICs help reduce this size, weight, and cost savings. For this example here, you can see that we were able to take a customer solution for a solid state drive from a solution size of 142 millimeters squared with roughly about 57 components and make it 80% smaller. And we were able to get that down to roughly 28 millimeters squared with 14 components. So we're able to provide all the benefits of a PMIC solution from a discrete solution down to a very integrated PMIC. But when you think about PMICs, they're kind of one-off and custom to a specific customer, because every system and every customer, they do something a little unique with the various voltage rails, various current levels, maybe sequencing on and off. Well, at Qorvo, we're able to take that a step further by making our PMICs truly multi-time programmable instead of one-time programmable. So what we do here with our active Qorvo SIPs technology is that we enable configurability. So SIPs stands for Configurable Intelligent Power Systems, which allows us to control the power circuitry and add some levels of configuration to it. Now, I'll touch in a little bit later on what configurabilities you can add towards your PMICs. But first, I'll start off why Qorvo Power for ICs. It's because we're configurable, multi-time programmable, and that technology that we have stated is what we call internally and publicly announced to everyone as active SIPs. With active SIPs, there's no special software, firmware needed to program the PMICs. We're able to reduce solution size and BOM count inherently through because of a PMIC. We could sequence external regulators, so if the PMIC doesn't have all the voltage rails that you need, it can also regulate other voltage regulators. The same part number can be used to support different SKUs. We could just change the configurations. These configurations are just a 3-digit suffix at the end of the base part number. We call that at Qorvo CMI, and I'll touch on that in a little bit. We're able to do bench test devices and get to fast time to market. So we're able to give samples if there's a PMIC already in a portfolio. We're able to give bench tested devices up to no more than 50 devices, roughly within 2 to 3 weeks. And then time to market roughly between 14 to 16 weeks from whenever we establish what the configuration needs to be. And once we agree to that, we're able to get to production roughly between 14 to 16 weeks, which allows us, and on top of that, fourth bullet, we were able to get some level of ease of material management. And I'll touch on that on the next slide. So highly configurability, right? So no two customers' designs are ever the same. Well, Qorvo provides superior configurability compared to the competition. So we have the base part number, the ACT 88329, and let's say, we released the 101 as a mass market device, and you come to us and you say, hey, it's everything that we want besides maybe the sequencing to turn it on and off, and this GPIO, I want to have it to do something special, and the voltage rel is at 1.8, I really need it at 1.2. Well, we're able to create your own 3-digit suffix, or what we call it CMI, and create your own custom CMI to what your needs, and that would be your orderable part number. So it would be the same base part number, ACT 88329, and you have your own orderable, which is the -102. So now you'll be ordering 102. Now I'll get into the importance of that in the subsequent slides. So we can have one base part number, the ACT 88329, and have it be used for multiple customers or multiple system technologies or multiple iterations of your system. So here's an example of it being used for a thermostat, SSD, a thermal camera, a solid state drive, to a IP security camera, to a home, a Google Home Nest device, to a point of sale terminal. So various end applications with one PMIC that needed 3 bucks and 2 LDOs and some level of configurability. So not just one device can be used for multiple end equipments, it can be also used for multiple solutions that you may have. So on top of that, it allows for flexible material management. So it allows demand to be shifted between customers' different solutions. So let's say you have used the same PMIC for 3 generations of a system that you have developed. So we would give it the ACT 88420, we would have 101 is your first generation. Let's say your second generation is the CMI 102, and your third generation is 108. We consolidate your volumes for all 3 into one, accumulate all the volume into one base part number. So that'd be like 300,000 units. We generate all those orders onto however many wafers we need to support, those orders. But then when you're ready about to order and we're going through production tests, and that's where we program the CMI, your orders change from 101 to 102 all the way to 108. So your third generation became a little bit more popular, and your first and second generation are not doing well, and most of that volume is going towards your third generation, which is CMI 108. So we're able to do that fast reaction to your changing demands, and low material management risk, and then fast time for development for prototypes. And I'll touch on that in a little bit later. So how is this CMI programming done? Well, we use the ActiveSIPs programming tool, which with every device that we develop, we have a GUI that interfaces with that device. And how to interface it, we provide an ActiveSIPs dongle. So that dongle is connected to your computer through a USB port, and then that is connected to the EVK. And then this ActiveSIPs dongle enables you to debug, make changes to the PMIC default settings on your board on the spot. That is done through the PMIC, where it has non-volatile memory. And that non-volatile memory can be changed through the ActiveSIPs dongle. Now, if you want to do some prototyping, but on your board, if you look at the bottom right, that's how you would configure your board to enable the ActiveSIPs technology to be interfaced with your board. So all you really need is a 1x6 header with 50 mil spacing in between, and then we then you just need roughly 4 1x2 headers as well to configure your ACT PMIC. Now, with this dongle and with our GUI system, you can take any PMIC that we have in our portfolio and configure it to your needs, specific needs. And that level of customability allows customers to do quick prototyping. So if there's a PMIC that you see in our portfolio that's close to what you need, well, you could change the CMI default settings, the factory pre-configured, and use the SIPs tool to reconfigure the non-volatile memory and its default value. So when you turn it off and turn it back on, it's always going to pull from that non-volatile memory. So that means you could change the output voltage levels, power up, down, and sequencing on and off time delays, GPIO configurations, and a plethora of many other changes. On top of that, you could use the active SIPs dongle, or you can configure via I2C after power up with a plethora of many other configurations that you may need at some point. So a lot of flexibility, a lot of configurability just in prototyping. And then once you figure out what you want, or whatever CMI configuration that you want, then we'll work with you and then program that in production so that you don't have to use the dongle anymore when you're in production. It just works exactly the way you want it when you put it on your board in production. Now, there's some development steps when it comes to having a custom CMI. Stage 1 is suitable for engineering and development only. So that's bench test devices. So we're only able to give up to 20 to 50 devices that are configured to your needs. That means it's producible. That means we have the ACT 88420-101. That CMI 101 is what we released to the market. And let's say you want to do a different CMI. We agree on what that CMI is going to be and whatever configuration that is. And we provide you 20 devices or up to 50 devices that is producible. But the package is still going to be labeled as 101, but we give you samples within 20 to 30 weeks that's configured to what you have requested and what we agreed upon. It's not production tested. It's not fully trimmed specifically to your needs. It's not traceable, and it's not under warranty. But stage 2, it's suitable for qualification. That means it's production tested devices. However, the package may not be labeled as 102, which is what is going to be assigned to you for this development. It might still be labeled as 101. So therefore, it's producible, it's production tested, and it's fully programmed and fully trimmed to your needs, but it may not be traceable, and it's still not going to be under warranty. Once we vet our production test and qualify and we change the package labeling, that is when everything is in full rate production and everything is producible, production tested, fully trimmed, traceable, and under warranty. So overall, you can see that Qorvo is able to provide power PMIC solutions with reduced risk on supply chain through high levels of configurability. So we're able to leverage our building blocks to build these very configurable PMICs. But on top of after building these PMICs, there's still levels of configurability that you're able to take with you and configure it to your needs, which allows you once we find a PMIC that fits your needs, within 14 to 16 weeks, we can provide you from a CMI that we agreed upon and then provided you into production. We're able to configure to your needs, reduce board size and BOM reduction, ease on material management, and no unique software and firmware that is needed. Now, I know it's based on the poll that we have here. Let's see. I want to touch on a few devices based on the poll that everyone has submitted in the beginning of this. So most of you guys are, the poll here, I only see RF applications and asset tracking. So I'll touch on a few devices that could be unique for RF applications, and then I'll also touch on a few popular PMICs that we've seen for asset tracking and maybe potentially other solutions. So the first device I want to point out for RF applications is going to be the ACT, our ACT 41000. So this is just a RFPA drain regulator. So the typical applications that we see is that a lot of customers have a voltage in that needs to be down converted to whatever voltage that the power amplifier drain requires. So we have the ACT 41000 that has up to 40 volts in and is able to support any drain voltage from between 3 to 24 volts. So we have a plethora of devices that we have listed here, PAs, RF GaN PAs on the bottom left that it supports its drain voltage. So the ACT 41000 supports up to 96 watts and with very low power self-biasing. So 4.5 to 40 volts input supports up to 3 to 24 volts, up to 96 watts, and it's able to get up voltage steps of 12.5 millivolts and drain current up to 4 amps, up to 15.6 milliamps. And it does have an auxiliary LDO that supports up to 20 milliamps and then a self-biasing 5-volt regulator of 350 milliamps. So potentially you might have a self-biasing gas LNA and you might want to use a 5-volt regulator here as well to bias both your gas PA LNA and maybe potentially your GaN PA. We also have the ACT 43750 that I also want to point out. It's not a drain buck regulator, but it is an integrated drain switch driver and a gate bias regulator. So this device is for auto bias sequencing for GaN PAs. So it turns on and off the GaN PAs through its state machine logic. A lot of GaN PAs are very sensitive on how you turn on and off the GaN PAs. So you need to add negative gate voltage and put it at pinch off, apply the drain voltage, sweep the negative gate voltage until you reach the appropriate IDQ level, and then you apply the RF. So very unique bias sequencing required to turn on the GaN PA and to turn off the PA. So you just do that same sequence that I just stated, but in reverse. So this device takes all of that complicated sequencing and puts it into this device that does it all for you. So this device, the ACT 437, it's an auto calibration anytime after the field. It does the GaN sequencing and also provides some levels of protection. Drain switch on and off, pre-regulated by the DC supply, and it supports any drain supply input voltage from 10 to 55 volts, which pretty much captures, I believe, 95% of all GaN PAs. I know there's a few GaN PAs I've seen that are 65 watts, and maybe I think I said last year and a half, I've seen 100-volt GaN PAs. But outside of that, this supports majority of all the other GaN PAs that have voltages between 10 to 55 volts. The rise time, transmit, turn on and off rise time is roughly 30 nanoseconds. So I know a lot of people just want to use gate switching because of the faster transition times. Well, we're able to get down to 30 nanoseconds of transition times with this device if you use a GaN FET drain switch. The gate bias regulator has output voltage from minus 6 volts to minus 1.5 volts. And we believe the sweet spot for most GaN PAs is minus 4.5 to minus 4 volts. But we have a wide range with a 13-bit DAC that does a 732 microvolt steps. Output source current is 300 milliamps with a peak of 500 milliamps and very low noise of less than 200 microvolts RMS. So the bottom right is a block diagram of how it functions. So it's a gate driver. So it drives the voltages that is needed to turn on and off the drain switch. And then it auto generates that negative voltage that is needed for the GaN PA. And it does that sequencing for you, and then also turns on and off the drain switch as we've seen it as low as 30 nanoseconds. So here's a quick bottom right is like a high level block diagram of how the ACT 43750 would be used. But on top of that, we have a plethora of other devices that extend past the 43750 that can potentially replace a power brick that is used to power these GaN PAs. So the bottom right is just a simplified block diagram where you have a generator or a battery powering your bulky kilowatt power bricks. Then that power brick is used to power the GaN PAs and the rest of these RF modules. These power bricks can be very bulky in size because of these power banks and these large military standard or 1 millifarad capacitor banks. Well, with the ACT 43950 as well as the 43850, when you combine those two together, you're able to reduce your capacitor bank from 1 millifarad to 100 microfarads, which is significant in size. The 43950 is a constant current output regulator. So that means it's not a buck converter, so it doesn't pass down the voltage, but it provides constant current. So that means there's not going to be any EMI flowing upstream to damage the generator, and it provides that level of protection there. And with the 43850, it down converts, I believe it supports up to 100 to 200 volts, and it down converts that to 20 to 55 volts. So all these devices are in full rate production. You could find the data sheets and the devices at Qorvo.com. So if you and the data sheets are available if you through an NDA, but it's very simple through the online portal. And if you want any more details about these devices, on top of the data sheets, we're more than happy to have a full follow-on conversation with you. Now, I'm done with the RF applications, but I do want to touch on a few devices that I've seen used for asset tracking. So we do, on top of these devices that are used for power management devices that are used for RF applications, we do have a plethora of PMICs that can be used for numerous applications. We have a PMIC families that are low power, medium power, and high power. Some high power devices are used for power loss protection that are able to withstand up to 20 volts and also have an input voltage up to 16 volts. We also have devices that go as low as between 2.7 to 5.5 volts. So depending on what you need, these are very highly integrated PMICs. This portfolio is outside of the devices I just showed you, which are for power management devices for RF applications. So these devices here range in the number of voltage buck boost converters and a plethora of LDOs. Something I want you guys to take note of is when the third digit is the number of buck converters or boost converters, and the fourth digit is the number of LDOs. So this is something that we came up with when we were Active Semi, but now Qorvo, and we've maintained that numbering scheme still. The popular devices that I want to bring to your guys' attention is going to be the ACT 88321 and ACT 88329. It's a 3-buck, 2 LDO PMIC that supports up to 2.7 to 5.5 input voltages, and buck 1 supports up to 4 amps, but buck 1 can be used as a load switch. Buck 2 and 3, 4 amps and 2 amps respectively, and LDO 1 and 2 up to 400 milliamps. And then if the LDO 1 is used as a load switch, can support up to 1 amp as a load switch. And these are max current ratings that these PMICs are able to support. But through our active SIVs, you can really customize this to your needs. What makes the ACT 88329 and 321 special is that the 88329 is in a 2.6 by 2.2 CSP package with 30 balls with 0.4 millimeter pitch. And we notice a lot of customers do struggle with this pitch sizing. So with the ACT 88329, we removed 4 balls to fit in TH-vias for any PTH board. So we removed a few ground vias to add that spacing that customers have received, complaints that we have received to support their needs. The next popular device that actually I've seen for asset tracking and has been used for many other applications is the ACT 88420. It is a 4-buck 2 LDO. Buck 1 could be also used as a load switch, and LDO 1, LDO 2, and buck 4 both can be used as a buck 1 and buck 2. LDO 1 and 2 can be used as a load switch, and buck 4 can be converted into an LDO. A lot of flexibility here. It's very small. On top of the configurability, you can use 3-state GPIOs to make buck 1 as a load switch, buck 4 as an LDO, and LDO 1 and LDO 2 as a load switch, just based on the GPIO configurations that you have decided to use. So on top of the current PMIC configurability that we've said that you can configure with active SIPs, you can also have, with your GPIO commands, you can add that also another layer of configurability if you decided to do so. Another device I want to show here is our very highly integrated PMIC, the ACT 88760, used for highly integrated applications. We've seen it used for video, AR, or enterprise SSD applications. This is a pretty big device. It is 7 bucks and 6 LDOs. And again, the 3rd digit is the number of bucks or boosts, and the 4th digit is the number of LDOs. Wide input voltage range, 2.6 up to 5.8 volts of input voltage. And then small form factor of 3.85 by 3.85 in a WCSP package. Highly integrated, we have 10 configurable GPIOs for programmable system functions. We can add interrupt functions, reset, sleep, DEP, SLOP mode, DBS, fault detection, against any type of sequencing and control for any external supply rails, thermal protection, OTP, OCP, OV, UV, you name it, for this type of device. And then we also have our high voltage using for SSD applications. I'm not going to go through any of these devices that we have listed here, just because I didn't see anyone click on the poll that they have used these. But if you have questions for any higher voltage PMICs, we could touch on those a little bit later. Now I will open. I think that's the end of my presentation. And now I will open the floor for questions.
Thank you. Thank you for the excellent presentation, John. You did a great job. If we have any further questions, please feel free to reach out to your WestTech reps, and we will certainly relay the questions back and make sure we get anything further answered. I have posted a poll. If everyone could please respond if you have a moment, just to give us a little bit of feedback based on our presentation today. And thank you for joining us. We have recorded the seminar, and everyone will receive a link to the recording as well as the slide deck. So feel free to share with any of your colleagues if you think it might be of interest for them. And we hope that everyone has a great afternoon, and we thank you again for joining us.